this microphone here, but I tend to walk around a little bit, so if you can't hear me, just give me a big thumbs up or something like that, so that you can hear me. Can everybody hear me okay? Or is it okay? Awesome, thank you. So yeah, it's great to be back here at Adams State. I came here, I'll kind of go through a little bit of my history, but I came here not really with the intention of going into academia and research, but things change. So maybe that's going to be similar for you, or maybe you come here and you exit the exact same way you thought. But either way, I'm really happy to be here. We had a lecture series back when I was a student, much different topic, but there was a guy named Chris Bell from CSU up in Fort Collins, and I remember this presentation very well. So I hope you get something from here, and I have some ideas for master's theses. So if you're interested in that, you come talk to me or get my contact information from the last slide, and hopefully that inspires you for some projects. So how the next roughly 50 or so minutes is going to look like, assuming I don't talk too fast. We're going to talk about some, that first one's supposed to say background, but I guess some slides got mixed up. We're going to talk about isometric training in general, and then I'm going to share some results that are actually not yet published, but should be somewhat soon. Big meta-analyses as well as a randomized control trial, and I'll talk about what all of those things mean when needed. As for my background, Tracy kind of said a lot of it, so I can skim through this pretty quickly. But I'm from Calgary, Alberta, up in Canada. It's basically a straight drive north for about 2 days. And my very first job was as a cart boy at IKEA. So I was like 14 or something like that, and I'm just pushing carts around, putting them back in the stalls so the customers can find carts, and helping them load stuff into their car as well. But my first sort of foray into exercise science and strength conditioning was a private training facility called Peak Power Sports Development. So for the first couple of years, it was stocking fridges and wiping weights down and maybe cleaning up some spit valves on VO2 max testing, which is maybe something you'll experience if you are in one of Tracy's exercise physiology classes. All of that, kind of led me down that path. It's like, I like these time engaged things, I like these force plates, these jump mats. Let's kind of go down this road, an educational route. And I earned my first degree kind of as a combination at Mount Royal College and then finishing it up at the University of Calgary. And I worked for a period of time at the Canadian Sport Institute, which is basically the Canadian equivalent of the Olympic Training Center up in Colorado Springs. Once that opportunity ended, I ended up in Connecticut, and when I was there, I met a guy named Jason, who a few people in this room know. And Jason said, hey, we get along real good, and we're looking for some graduate assistants at Adams State. And I'm from Canada, so I'd never heard of Adams State before. But I was like, I kind of want my master's degree, and I might need it to kind of continue down this career path. So I already know somebody. So I came here sight unseen, and it was a little smaller than I was expecting. But I had a really wonderful time, and of course I wore the green specifically for Adams State. Next week when I do another talk, I'll probably wear some red or something like that. And it was really here where everything kind of changed. So I came in as a strength conditioning coach. Then, thanks to Dr. Robinson and the department, I got some teaching experience, and of course got to do some master's work. And I thought, I really like this stuff, and let's kind of go all the way. And so I did. Now, we'll see if this plays, but this is Plackey Hall. You might be aware of it. You can kind of see in the background. But we received a grant, and we purchased some force plates, which are still being used in some research studies. And I'm pulling on a bar. I cannot move. This is my first sort of experience with isometric testing. So we got some force plates under there. You'll see in a second. We got Matt Gersick, who some people might still remember, and we're looking at how much force I can put into the ground by pulling up on a movable bar. So it's a real pure test of full body strength. There we go. And that was part of one of the big publications we got from that master's degree. After the master's, I went back to Canada. I'm applying for scholarships, and kind of in the meantime, I'm volunteering in neuromuscular fatigue lab, and I learned about using isometrics. So I'm trying to push with my quad to get something that will not move. And I've got all these electrodes hooked up to my legs to measure muscle activity. There's basically I'm getting a shock or a jolt to my femoral nerve, so I kick a little bit harder. And I've got that cap on so that they can stimulate my brain. And they're doing a whole bunch of crazy stuff to me, and I did this to other participants. It wasn't exactly the research I wanted to do, but luckily I was also working with the football team as the head strength and conditioning coach, trying to see if there was ways to incorporate isometrics in a training environment. And there were many ways, which I'll kind of get in. And eventually I ended up in Auckland, New Zealand for my PhD, and we looked at a lot of different things, how do you do an ultrasound imaging of muscles, looking at qualities, size, composition, what's actually in the muscle, is it fat, is it connective tissue, is it actual contractile elements, as well as some side gigs where we were looking at power clean performance, again, how much force is going into the ground, how much force is going into the bar. Finally, before starting the before landing my current position, came back to Canada during COVID and worked in a sports medicine facility, strength conditioning, as well as some rehab. So we had some surgeons, we had some athletic trainers or athletic therapists, more strength conditioning coaches, did injections, surgeries, all that kind of stuff. So just kind of an example, we've got a guy who was in rodeo, and he was actually competing here about a year ago, so I made the trip and saw him and hung out with a couple of people I know here, and he got bucked by a bull, smacked his knee into a railing, like one of the barriers, and he shattered his patella. So you try and see what kind of exercises can you do, and how can you progress this kind of stuff over time. And some of that work involves some isometric testing, where we're trying to get stronger. I know you can't read that, but it's just a whole host of different testing metrics. Range of motion, power, strength, force, and isometric training can play an important role, especially in those clinical scenarios. As for some of my current projects, again, there might be one or two things here where people in the room, I know Adams State actually has a new ultrasound unit, relatively new, but we're looking at skeletal muscle assessments and how those types of things can relate to physical function. So we do a lot of work with older people and clinical populations, whereas Adams State has a lot of access to many different sports. So if you think you might want to see what muscle is made up in different sports, you can come talk to me at another time and we can get a good master's project rolling for you. The main topic of today is going to be the international collaboration I have with people in Singapore and most in Australia, looking at these pulling versus pushing isometrics. Now, resistance training in general is very important, and we have a ton of benefits, way more benefits than I could possibly fit into a 40-minute talk. But running is great, swimming is great, all these things are amazing for your heart and your lungs and your muscles and your joints. But at the end of the day, if you're not performing at least some resistance training, you're probably missing out on some big benefits. One of my passions or big interests is going and looking at different contraction types. So there are three primary contraction types. We have concentric, where the muscle is shortening, where you're typically going to be lifting things. So when you stand up out of a chair, your quadriceps, your glutes are working in a concentric manner. Eccentric is when you're lowering, so sitting down into a chair or going down into a squat or lowering a dumbbell during a bicep curl. And then isometric, there's no movement going on. You might push really hard, the muscle might shorten a little bit, but the tendon will lengthen a little bit as well, so there's no real change in your joint angles. And they all have their different strengths and weaknesses. I'm not going to talk about this entire table, but in general, the concentric movement tends to be better for building power and sports performance, speed, and jumping, because it's a little bit more similar to those things. Whereas the eccentric has an interesting component where you're lengthening little bits of your muscle called sarcomeres under force, and that tends to improve muscle size and does help with strength quite a bit. Isometrics lie a little bit in the middle. We're very good for strength, maybe not so great for hypertrophy, but the big benefit is that we can control that range of motion to very specific joint angles or muscle lengths. Sometimes that's important for sports, but it's also very important if you're dealing with like orthopedic injuries, for example. If you're doing a knee extension, your knee might give you pain here, but it might not give you pain there, or vice versa. So you can kind of lock a machine or a setup into a specific joint length where you can actually perform good quality work and help your muscles and help your joints and help your strength without irritating the injury. Now I included this image and the one on the next slide because it's the earliest thing I could possibly find for studying muscle under isometric conditions. So this is a textbook, and it was published in 1895. And the first example, I'm not going to read this off, but it's from a study that's actually even older than the book. I actually have no idea how old that study is because it doesn't cite it properly, but at least as old as 1895. And this researcher, Adolf Fink was his name, took a single muscle fiber from heart muscle, and he tested this thing under isometric conditions. He probably used a lot more than one cell, but a lot of research has been done in that way to help us understand the microscopic level what's going on during muscle contraction. And at the end, what we see is a relationship between how fast you move and different force velocities. So if you're moving really fast in a constant velocity, you're not going to have a lot of force. It's like trying to jump. You produce some force, enough to jump really high, but it's not nearly the same amount of force as you get when you're pushing against an immovable object and you have several seconds to kind of build that force. And that's what an isometric maximum is. You can also get a ton of force from fast eccentrics under maximal efforts, but those are questionable in terms of safety. You can imagine loading, 500 pounds on a back squat, or maybe 800 if you're already able to squat 500. Some of the big football guys might be able to. And you're trying to lower this huge weight under control. And for the most part, you're not going to be able to do that safely. And that's where isometric training and testing is kind of a nice, sweet middle ground. You get maximal force, or close to maximal force, but also with near maximum safety. And we can test isometrics in an isokinetic dynamometer, which is set to either move or not move and record force, a strain gauge, or a force transducer, and you can set that up with like that mid 5-volt setup that I illustrated in that video a little bit earlier. There's also some really cool machines coming out. So this is called a force frame. That's actually the guy who had the shattered patella. And you can take this machine, you can rotate it and change the orientation on the pads, lift and lower it, and then you can test groin strength or knee extensions or elbows or shoulder rotations. It's really quite a remarkable piece of equipment. So using isometrics for training, testing, and rehabilitation is just becoming increasingly more common every single year, in part due to technology. And we have a lot of books and examples of this. So we got an older book called Super Training from an old Russian guy who came to the United States in the 70s, I believe. And then we got a little bit more modern book on the right, the triphasic. And that was one of the first books that actually recommended even training eccentric, concentric, and isometric separately. So you do like a couple of weeks of one, a couple of weeks of another, a couple of weeks of the third, and then cycle. Now I don't necessarily endorse that, but it's just kind of interesting how things have kind of progressed over the last 40 years. And the first publication that came out of my PhD was looking at different types of isometric training, so different muscle lengths, different intensities, how hard you're pushing, and different things as far as what you are intending to do, even though you're not actually producing any movement. And in general, there wasn't a lot of studies, so each one of these data points is a different study. And on the x-axis, we have the length of the muscle, or the elbow, or knee, whatever that particular study happened to look at. And on the left side was how much that muscle grew over an intervention period. So questionable number of studies, but we see a little bit of a slope, where the longer you train a muscle like that, the more muscle you build. And there's many reasons for that. This particular image is looking at training intensity, or how high of a percent of your absolute max effort you're putting in while you're training. And then on the left again, we have muscle size, and that relationship is a lot more flat. So assuming you do the exact same amount of total work, it doesn't seem to matter how hard you push. So if you push as hard as you can for 3 sets of 5 seconds, that's 15 seconds of work, versus 50%, but you do 30 seconds of total work per session, the amount of hypertrophy is almost identical, or at least insignificantly different. However, this one is again looking at intensity and strength this time, and there's a little bit more of a slope. So working hard, pushing with a lot of force is generally going to be better for strength, relatively self-explanatory. And even though there are not a lot of studies here, a ton of other reviews looking at like dynamic movement, not just isometrics, tend to support the exact same things I mentioned in the last few slides. So there's a lot of evidence out there again. If you want to build big muscles, train through a full range of motion. If you want to get strong, you got to lift heavy weights, basically. Now on to the real bread and butter of the presentation, including a lot of new data that isn't yet published. We had holding versus pushing isometrics. And the first study that really came out that kind of floated around social media and made everything a little bit more popular than it already was this study. And you can see 2017, relatively recent, and even though there's a lot of studies actually comparing pushing and holding from as early as I can find 1995, it didn't really take off until this one. I think some of that has to do with like Instagram and Twitter and these types of things. But I think a really important lesson for a lot of you, especially if you plan to do a master's and maybe publish something eventually, is this title is very explicit in what they did. They looked at different contraction types and different types of isometric rates. Whereas if I look back at the studies from the 90s and the early 2000s, the titles are not very good, okay, to put it frankly. They're very, they're mild. They're not saying we really did this, like, oh, we looked at two different tasks. But on the isometric task, what are the two different tasks? So a little take-home point there is be really explicit with the titles. Whether that's any kind of projects you're working on, make sure the person reading them knows what they're getting into and can find it. Either way, these German people, researchers, looked at several people, and they had electrodes on their triceps, which is the prime mover muscle, as well as some of their accessory muscles of the shoulder and of the abdomen. And they had this piston, and depending on the situation, what day they're testing them on, that piston is either going to try and move them, or that piston will be completely still, and they will push into it with the same amount of force as that piston was trying to move them in the other session. So in that way, they're testing pushing versus holding. Complicated chart, but basically the take-home point from that result was that they are different neurologically, in that when you're pushing against that still object, the prime mover muscle tends to be more active, and when you're trying to resist being pushed against, a lot of your accessory muscles are going to be a little bit more active. So very similar looking task, and in fact identical when you have the still image, but the way the brain and the muscles act is going to be at least a little bit different. So I saw this paper, a couple more like it, and at this point I did not yet have a full-time academic position. I'm kind of searching around, and at the same time I know that having more publications and more connections is going to help me kind of accomplish my goal. So I'm at home, but I'm training people during the day, and I might be teaching a class or two here and there, but I'm like, I got to keep publishing. So let's put a team together, and let's go right to the top of the quality of evidence hierarchy, and let's do a systematic review and maybe a meta-analysis depending on what we find. So I put together this great team, and I'll list off all the names on the second to last slide today. But cool enough, after about 2.5 years of effort, we finally put out a preprint of this massive, huge systematic review, and it's the longest thing I've ever written except for my master's and PhD thesis documents, but it's very, very big. We have to cut it down a little bit actually. But you can scan this QR code that just became available in 2 days. So this is really cutting edge stuff, and it'll take you to a link of the non-peer review version of the document. But we can see a couple of different examples. Systematic review, we're gathering studies that already exist. So we're going through our libraries and we're finding every study that we can that is relevant and fits our inclusion criteria. And we found 54 studies that directly compared pushing and holding kind of in a similar manner to this one. Some examples just for visualization, we got some knee extensors, so there's this chain attached to the ground, there's the strain gauge or force transducer, and they cannot move this thing. No matter how hard they push, it will not move. Whereas in the holding one, they're suspending a load, and they're trying not to let gravity pull their knee into further flexion. Similar idea with elbow flexion, and even small muscles of the fingers have been examined. Here was our search terms. We found about 6,000 studies with our search terms. We had to go through all of them based on the title and eventually the abstract. And eventually there was actually a couple we didn't find even in all of those studies because the titles are so bad. But eventually we found 54 studies that we were able to include. The power of the meta-analysis is that you pull all these things together and you end up with a sample size of 856 participants, which of course is far beyond what you could ever get with just one single study. So you're able to pull a lot of this data together and have a very strong view of the overall literature. A lot of different muscles, mostly biceps, a little bit of quads, and then a lot of other muscles. There's also some trunk extensors or back extensor tasks, two studies, which I'll kind of touch on specifically in a couple of moments. One big limitation was that the average intensity of these studies was only about 35% of maximal exertion. That's good for these studies because it gives a little bit more time where they can hold these contractions and they can study differences. So it's great for research, but if anybody here has ever like lifted weights with the intention of getting strong or big, you know that 35% of maximum is generally not going to cut it, except for maybe the first couple of weeks if you're an absolute beginner. So just kind of putting that forward, that some of these evidence is based on studies where the training intensity is not particularly great for practical application. Another step is assessing how good are these studies. We don't want to put them into a big funnel and mix them all together and see what comes out. If they're bad studies and they're not done well, luckily the overall risk of bias assessment was pretty good. The studies were very solid, and actually one of the really cool things was with this, as well as the methodological quality assessment we did, was that the newer studies tended to score better. So science as a whole tends to be getting higher quality. Stuff from the 90s and the 2000s was probably great for its time, but when you compare it to gold standard type testing and reporting guidelines, it's getting better almost every single year. So that was a really cool thing to see. This is not from our meta-analyses, but I just want to quickly go over what you're going to see on the next slide so you might have a better idea of how to interpret it. This is an example of a forest plot, which is the most common way of presenting meta-analyses statistics. On the left side, we have the individual studies. These are all different studies, and we have some sort of an effect. So this could be, for example, the effect of a new pharmaceutical on a specific disease or on inflammatory markers, or it could be the effect of the two different training modalities on building muscle. It doesn't really matter. The bigger squares tell us that these studies have a lot more participants, so they're going to sort of have a larger overall effect on the meta-analysis output than these studies that might have only had 5 or 10 participants. If these ones had 50, they're weighted more, they're heavier in the overall equation. And then at the very bottom, in that diamond, we have, well, what is sort of the average weighted effect of all of the studies you're including in these numbers. So the first thing, we got a bunch of different types of output. The first kind of category was performance and mechanical variables. And this is probably for a lot of people the things that are most interesting, I suppose. The first one we have is time to task failure. So if they're producing, hypothetically, 50 pounds of force against something that will not move versus holding a dumbbell that weighs 50 pounds and trying not to move it. So the intensity is the same regardless of whether it's the pushing or the holding condition. Now, what we see in this, we have a whole bunch of studies that contribute to that overall effect. And the overall effect is actually quite strong, an effect size of 0.74, which is moderate to large, which means that it's pretty noticeable, okay? It's pretty noticeable. And that's in favor of being able to maintain the pushing contraction where you cannot move. You can hold that longer than holding a dumbbell that's trying to move you, okay? We'll kind of get into what that means in a little while. Now, if you're really paying attention, and if you have to be really paying close attention, you might notice this block down at the bottom. So this is the back extensor or the trunk extensor muscles, and we see those studies are way off to the right side of the graph, way away from all of the rest of them, basically. So when people were put in that same type of condition, pushing versus holding, but they were using their postural muscles of the butt and the lower back, and maybe their hamstrings, the effect was actually the complete opposite. They were able to maintain the holding contraction far longer at a really large magnitude for the holding. And that magnitude, by the way, was 2.36, which is like almost unheard of in research. That's an extremely large effect size. That would be like getting every member of the football team to increase their squat by like 100 pounds or something, if we're trying to give it another example. And that just kind of tells you that the muscles of your arms and legs that are actually propulsing you and lifting you out of chairs and walking upstairs have a different neural strategy than the muscles that are just keeping you upright all day when you're sitting in a chair, standing, walking, doing any of these other tasks. They're trained to resist gravity as opposed to kind of lifting you up. These are called meta-regressions. Basically, we're looking at if training intensity or the size of the muscles has anything to do with what we saw in the last slide. And because these lines are almost completely flat, we can say that training intensity and the size of the muscles studied in each of those individual studies had really no effect. It didn't matter whether it was a big muscle of the quad or a little muscle of the fingers. This effect was still basically the same. The next one is ratings of perceived exertion. How difficult does it feel? How difficult does it feel? Typically this is on a 1 to 10 scale, although there's a 1 to 24 scale as well. Basically, there's no real difference in how it felt at the very beginning or at the very end, but during the middle portion, it did seem to feel a little bit more difficult during the pushing. So that's a little bit interesting. If you can't hold the holding quite as long, why does the pushing feel harder at the midpoint? And that's because the time that they're holding is different, so the midpoint is different. So we have to look at these a little bit differently. Again, there's a meta-regression, but this is the rate of increase. The rate of increase of the rating of perceived exertion. So how much faster does it start to feel harder? And almost all the studies are on the right side of 0, telling us that it started to feel harder a lot faster during the holding. So that kind of makes sense given what we know about the time to task failure. The next sort of section that we kind of quartered the results off into was the cardiovascular and metabolic effects. So this includes things like heart rate and blood pressure and oxygen uptake and glucose uptake into the muscles, things of that nature. So heart rate, we don't see much again. At the beginning, at the middle, at the end, there's not really a whole lot of difference between these heart rate measures. And a lot of that is probably due to the fact that a lot of these muscles that we're testing are relatively small. Again, fingers are involved, calves are involved. So it's probably not going to get your heart rate up all that much. Maybe the quads might, maybe the back extensors might, but either way, you're still looking exclusively at single joint movements. So heart rate is not going to be massively affected. Blood pressure, kind of a similar story. When we get to that 0.18 range, you're starting to look at maybe a small effect, although it's still close to trivial. So maybe blood pressure is a little bit more affected by holding contractions, perhaps. We look at the rate of increase again in heart rate and blood pressure, and once again we can see that we end up with a faster increase in heart rate for holding and for blood pressure for that matter. So it's more time efficient. If your goal from these isometric contractions is to work the heart or to work the vascular system, it's going to be faster for you if you're performing holding isometric contractions. And I'll kind of get to why basically right now. As far as the other metabolic effects like tissue oxygenation and blood glucose uptake, no real difference in tissue oxygenation. However, the holding resulted in faster glucose uptake. So here's an example from one of the studies that was included in the analysis. And we have, they call them different things. Instead of HEMA and FEMA, they call it a force task versus a position task. A position is holding, force is pushing. And what we see in the position task is there's a lot more light, right? It's more visual, there's less blue basically. And this is just telling us that more muscles are active. It kind of goes back to that first one with the piston, and the accessory muscles are more active during the holding versus the pushing, the front mover muscles. So you have more muscles that are working a little bit harder in the holding. And this is likely because when you're holding something, you don't want to push too far and lift it, because the researchers have said, hey, don't lift this weight, just keep it there. So sometimes the bicep's going to twitch a little bit and try and lift it, but the tricep's going to kick in and say, don't lift it. And the shoulder has to stay steady as opposed to pushing against something that's rock solid. So there's more degrees of freedom when you're training the holding. And that's probably what we're seeing here. And probably also contributing to a lot of the other things I just presented. As far as the neurological thing, the brain and the electrical activity of the muscle, this was a little bit of a problem for us because of just a massive variety of different variables and collection methods. So there's surface electromyography, there's needle electromyography where they actually take a really small wire and they insert it into the muscle through the skin, through the fat, and measure what that way. There's TMS stimulation, there's that nerve stimulation that I told you I went through in that one study that a couple of slides ago, and that's quite painful by the way. And then there's a lot of different ways of processing. So we were not able to do meta-analyses on the neurological variables. There was also some really interesting sort of special studies. So experimental joint pain, I'll talk about that in a minute. And then other things, residual force enhancement, as well as being in like a hot versus a cold room. Those were things that we couldn't really pool together. There was one study in each of those. So a little difficult to synthesize results in that case. However, generally speaking, even though I can't give you a precise number or magnitude, the trend was that, again, pushing the agonist or the prime mover muscle is more active. There's bigger or larger amounts of electrical activity in that muscle, whereas in the holding, it's a little bit more distributed to all of the other muscles around the main joint. And the last thing I'll mention, even though it was only 2 studies, they used experimental joint pain. So what that is the researchers are taking a syringe full of like a saline solution, and they're injecting it, in those 2 studies case, into the knee. It wears off really quick, but for about 2 hours it feels like you have arthritis, or it feels like you have tendonitis or something like that. So you're irritating the joint, you're bringing in inflammation, and now you're able to study people who don't have an injury, you're not worried about exacerbating an injury, and you can study them as though they were injured. So a pretty cool bit of research going on there. What I will say, even though it's only 2 studies, brain activity and neurological activity were less affected from the injection when doing a holding contraction versus a pushing. I'm not sure I can really explain to you why that's the case. I'm not a neurophysiologist, but I think that's really cool from a rehabilitation perspective. If a pushing isometric contraction is giving somebody pain through every part of the range of motion, well, maybe try a holding isometric and see if they can tolerate that and build strength there before maybe after a week or 2 going into a different training strategy. Now, we do have a training intervention. So this is the second bit of new information that is also not published, but will be hopefully, fingers crossed, very soon. And this is the first training intervention out of all of those 54 studies. All 54 were just kind of cross-sectional, quasi-experimental things that didn't track this period, people over a large period of time. It was a 1 session in, 1 session out, analyze the data type of thing. And this is the benefit to reaching out to other people to collaborate, because one of the researchers I invited to collaborate on the meta-analysis invited me to collaborate on this one. So, this was completed at the Singapore Institute of Sport. Relatively small sample size, but within participant group, we had 10 participants, 5 males, 5 females, so a balanced group, although somewhat small. And each leg was dedicated to training for 6 weeks, 2 training sessions a week. One leg would train with the pushing isometric muscle actions, and the other leg would train with the holding isometric muscle actions. There's a little bit of limitation there, but it's great because you can essentially double your sample size quite easily. So this person's an isokinetic dynamometer. You can load it in a bunch of different ways, but for the sake that you're looking at, it's going to act very much like a leg extension machine you might find at a regular gym. Before and after the intervention, we measured all these things. So we measured strength, peak strength, concentrically, isometrically, and eccentrically. So we got a nice little battery of strength testing. And we used ultrasound imaging to measure the muscle thickness of all 4 of your quadricep muscles. We were also able to splice some images together and get the length of a muscle fascicle, which is basically a bundle of muscle fibers or cells, as well as the angle that they attach onto the aponeurosis, all of which have at least some carryover to speed or strength or force production in different ways. And now the main results, this is from an ANOVA table, which has some strengths and weaknesses. It's a very robust statistical test. It's really immune to having false positives, which is great. Now, the main thing is this one. Well, there's actually 2 main things, I suppose. The first one is this. And that tells us that both groups improved by a pretty significant margin improvement for both legs, I should say. So everybody improved, or at least if everybody did, the groups as a whole, when analyzed together, improved in all the variables. I guess unfortunate, because it's not crazy exciting, is that there's no statistical difference between the legs. So both legs improved, but one did not improve substantially more than the other. At least we're looking at no p-values. However, if we analyze those things with a slightly less robust statistical test, t-tests, and effect sizes, which tell us the magnitude of effect, not how consistent it is, there's some interesting things to look at in terms of like trends, I suppose. So this figure is looking at strength. So we have concentric strength, eccentric strength, and isometric strength. Each one of those dots is an individual participant in each group, or an individual limb of each participant. And I can't quite remember off the top of my head, but the diamonds I think are women, and the circles are men. Now, the main finding here is that the pushing actually had a little bit more strength improvement regardless of the muscle action we're testing here. So our hypothesis was that holding would be better for eccentric strength, because it's a little bit more like eccentric strength. But we were actually wrong. And that might lead back to that greater neuromuscular activation when doing pushing that we saw during the meta-analysis, right? And all those other studies we looked at. As far as muscle hypertrophy goes, a similar trend where when we look at the ANOVA, there's no big difference between groups. However, we can see that the holding muscle action resulted in slightly greater hypertrophy for all four quadricep muscles. And the biggest statistical difference, which actually was significant based on the t-test with a moderate effect size, was the rectus femoris. And I think that's because the rectus femoris is this muscle right on the front of your quad. It's quite narrow. It's the only one of your quadricep muscles that crosses both the knee and the hip. So it acts as a prime mover and it acts as a stabilizer. So going back to a couple of slides ago where I said the stabilizers were more active during holding, that possibly is why the rectus femoris had the largest difference in hypertrophy between the two contraction types or muscle action types. There were no real differences in muscle architecture, that fascial length or the donation angle. However, again, the patella tendon, that was a moderate effect size with a significant t-test, telling us that we actually were able to make our patella tendon a little bit thicker, a little bit faster with the holding isometric muscle actions. Now, kind of take away from that study, and you combine that with the meta, pushing probably better for strength and performance. So if your goal is to run faster, jump higher, be able to push people on a football field a little bit better, doing pushing isometrics as part of your training program is probably going to be a little bit more efficient. On the other hand, if your goal is tendon rehabilitation or building muscle size, then incorporating holding isometric muscle actions might be, again, a little bit more efficient use of your time. Once again, I just have to point out that relatively small sample size and the intra-limb study design, there's a little bit of a crossover effect that happens, especially when it comes to strength. So that might wash out a little bit of the differences. Just to kind of elaborate on that a little bit further, if you happen to be in a cast, like you broke your leg or something like that, or you couldn't use your right leg for, let's say, a couple of months or several weeks, it's probably still a good idea to train your left leg, because then when you get out of the cast, your right leg will be stronger than it would have been if you didn't train your left leg. Because your brain is still used to controlling your leg muscles with intensity. So that's a whole other topic. So again, the cool thing I thought was that randomized control trial, or the training study, really lines up with what we found looking at all the acute data in that systematic review and meta-analysis, right? So pushing, greater agonist activation or prime mover activation, which leads to greater strength gains. Holding, more co-activation, larger metabolic effects, less blood or more blood flow restriction. Those types of things can lead to muscle hypertrophy. So at the end of the day, pushing for maximal strength and sport performance, holding for rehabilitation and maybe some muscle building effects. As for future directions, I think this is kind of a cool topic. I enjoy talking about it. So I do have some ideas for studies, and that would include having studies of multi-joint or closed chain movements, right? Incorporating several joints, more functional movements, deadlifts, back extensions, squats. You can see some examples here. Larger sample size, of course, the higher intensities, because the vast majority of the research is on like 30% max. And looking at more intermediate clinical populations, people with bad joints, arthritis, these types of things. I do, by the way, hope to apply for a couple of different grants. There's a brand new one from NSCA. It was announced like 2 weeks ago. It's called Laboratory to Field. And it's for things that have been shown in a laboratory setting, but not so much in practical settings. So I think this particular topic will be a strong consideration. So hopefully I can actually maybe pay a master's student here or elsewhere. But that's questionable, at least at this stage. So basically done. I just want to have a little bit of shout out to people who helped me with this presentation, as well as those 2 studies that I presented on. With Andre Nelson, who's a really good buddy of mine. He was one of my PhD supervisors in Melbourne. During COVID, he let me live with him for like 6 months rent-free, because I was a poor student, so awesome guy. He's at Victoria University in Melbourne. We have Danny Lum, who's at Latrobe, as well as the Singapore Institute of Sport, and he earned his PhD who has been in the Young Technical University in Singapore, as long as with his 2 professors, Xiao Chen and Piao Gong. And we have Alex Natara, who's a head strength and conditioning coach at the New South Wales Institute of Sport, which is in Sydney. And finally, Frank Dittman and Laura Schaefer. I've reached out to those German researchers from that study, and they contributed a lot, and they're at the University of Potsdam in Germany. Again, there's that QR code if you want to read a little bit more, my contact information. And I also saw a LinkedIn page like 2 weeks ago that said, don't just have a slide that says questions, you want to have something that people will at least enjoy looking at, even if they don't have any questions. So here are some animals in my life. So I live with the 3 cats, including that one who's almost 21 years old. And then that's my girlfriend's dog, Quincy, who's a very good boy. So that's going to be up, and I can take some questions if there are any. So there's a couple of things that you need to keep in mind regarding isometrics. And that, yes, they probably will not carry over to high performance sport in the same way as lifting through a full range of motion with a barbell or a dumbbell or some other sort of machine. However, they do have a place in sports performance settings. So for example, Alex and Danny are pretty high level guys at Singapore Institute of Sport, New South Wales Institute of Sport. They incorporate maximal isometric training with almost all of their athletes, just to different degrees. So isometric training is amazing at recruiting maximal amount of motor units. So this is something that can be used to kind of break through a plateau. So if somebody is gotten pretty strong, they're not getting strong anymore, they might need to learn how to neurologically activate more motor units, and maximal, especially pushing isometric muscle action is a great way to kind of connect the brain to the tissues. So it's probably a nice way to include that every handful of weeks, 1 or 2 sessions, or for an activation type exercise. So there's another concept called post-activation potentiation, where a maximal effort followed up a few minutes later by a ballistic effort, like throwing a med ball or jumping maximally. You can often see fairly substantial increases in that dynamic force production a few minutes following maximal activation, which is maybe best done isometrically.
So I'll ask a question in line with my colleague, Dr. Robinson. So typically, when you're out of season and you're in a would isometric, an isometric regimen incorporated with the maintenance that normally goes along as an adaptation to in-season, how might that enhance performance? Because what typically you do see is over the course of the season, people's weight room performance goes down no matter how well the program is designed.
Yeah, well, that's a good question, Ed. And I think there's a nice place for isometrics in season as well. So even though it might not carry over necessarily well to dynamic performance, another really big advantage of isometric training is that it tends to result in little to no muscle soreness, and again, very safe for your joints. So we know football athletes or any athlete in season, volleyball or swimming or anything like that, the joints really take a pounding, and they're sore from games because they're getting hit and they're having to absorb forces from players. So when you train them, the last thing you want to do is make them more sore, but you still want to activate the muscle as best as possible, bring blood into the muscle, and because there's no active lengthening in a muscle contraction, the amount of muscle soreness that results is again very, very small. So we can still actually train with maximum intensities, but it will not, or almost certainly will not result in additional muscle soreness. Thank you. Yes?
Did you guys keep track of what the participants were eating? Because I know nutrition has a.
I'm sorry, I can't really speak up a little bit.
Did you guys keep track of what your participants ate? Because I know nutrition has a big role in muscle building and recovery.
So the question was if we tracked our participants' basic food or dietary habits, which is a very good question because, of course, that can definitely make a difference. There's kind of two answers to that, two parts of that. One is no, we didn't. So that is potentially a limitation. However, in that particular study design, because we're training both of their legs, and those are different groups, the one leg gets compared against the other. So whether they're eating a lot of protein or not that much protein, the effects between the legs shouldn't be affected by dietary intake. So another benefit of within participants design. But yeah, definitely something to track if you're using separate participants in each group.
Anyone? Any more questions? Y'all are football players back here.
Sure.